I'm going to discuss a sample problem about thermodynamics and heat transfer. This topic is in Chapter 6, the vapor power cycle and gas power cycles. So here's the example. Consider a closed system Carnot cycle that uses 0.002 kg of air. The cycle's temperature limitations are 200 and 600 Kelvin, while the cycle's minimum and maximum pressures are 30 and 3000 kilopascal respectively. Find the net work produced by a cycle while assuming constant specific heats. Then we have here the maximum and minimum, the minimum temperature limitations, and the maximum limitation. So in the given, we have here the mass 0.002 kilogram. The pressure 1 is equal to 3000 kilopascal. Pressure 3 is equal to 30 kilopascal. And the maximum temperature is 600 Kelvin and the minimum temperature is 200 Kelvin. The specific heats can be found in table A2, so you'll just get the corresponding CP, CV, and the R, and also the compression ratio that is given in the table. So next slide is the minimum pressure in the cycle is P sub G, and the maximum pressure is P sub 1. So here is the equation for that. So because it is given the pressure sub 1 and pressure sub 3, so let's just use this to get this pressure sub 2. So we have this equation. P sub 2 is equal to P sub 3 times T sub 2 over T sub 3 raised to the K over K minus 1. So substituting all the given in this equation, we have this number and calculate it all, and we'll get this final answer 1403 kilopascal. The heat input, we have this entropy change, and just copy the value of R and the pressure here, the pressure 2 and the given pressure 1. So calculating this, we have this final answer 0.2181 kilojoule per kilogram times Kelvin. Because of that, we'll get this heat added by this equation, the mass times to the temperature maximum and to the entropy change. Substituting all the values from that equation, so we have this, the mass, maximum, temperature, and this entropy change. So calculating this, we'll get this answer 0.2617 kilojoules. So to get the thermal efficiency, we have 1 minus the minimum over the maximum temperature, and substituting that, and we'll get this 66.7% thermal efficiency. So we're gonna get the net work produced by the cycle. So here is this equation. So the thermal efficiency times to the heat input. So we'll get that. So this percent, we converted it to decimal. So we have 0.667 times to the heat input of 0.2617 kilojoules. So we got this final answer 0.175 kilojoules. So that's it.